Hello friends. In this video, I will try to give a recursive relation of volume of hyperspheres of different dimension. I did a previous video where I founded explicitly the volume of a hypersphere, and this relation can be directly obtained from that answer that I got. So the volume of a hypersphere embedded in n dimension of radius r we obtained was this was the volume that we obtained. So where tau is the gamma function, so tau of n plus 1, so tau of n plus 1, so tau of n plus 1 is n factorial. So let's see. So I will follow a different method in this one. So let's write it in a notation wise. So volume of a radius r embedded in dimension n. So this volume is simply nothing but this integral. It is this integral, but subjected to a condition over the limits of integration, that the limits of integration must vary as should be less than equal to r square. So this is the definition of volume. This is what volume is actually. So you don't want to give integration limits where you are not on the sphere. You are getting out of the sphere. So this is the volume. So now let's make a change of variable that x equal to r times y. So x equal to r times y. This volume becomes what will be this volume become? So look, I put x equal to ry. Each of the x becomes so r square jumps out, cancels this one. Okay, so and here dx1 to dxn, so you get a r power n, and they become dy1 to dyn. So if you see, what I get is this. Okay, so volume of a n-dimensional sphere of radius r is related to radius of 1 unit by this relation, by stretching it along like in all direction, which is intuition that we all have. So this was the intuition that we proved just now. So now let's see. So volume of one dimensional of so in n is nothing but this integral subjected to x1 square plus x2 square dot dot till xn square less than equal to 1 dx1 dot dot dxn. Okay, well, so this can be written like this: double integral of x1 square plus x2 square less than equal to 1 bracket. So I take these two, x1 square plus x2 square, on that side. Okay, and so within the bracket what I have is x3 square plus x4 square dot dot xn square less than equal to 1 minus x1 square minus x2 square. So I mean these all are integration. Okay, so this is this integral inside will be subjected to this condition, because this was the initial condition. So and then here I have dx1 dx2, I have dx1 dx2 here, and here I have dx3 to dxn. Okay, So I just rearranged the integration. I just splitted the integrations. So, but now see, an interesting thing has happened in doing so. This can be written as 1 dx1 dx2 v under root 1 minus x1 square minus x2 square of n minus 2. So you see, in doing this thing, this entire thing inside the bracket is actually volume in n minus 2 dimension with this radius, because you see the part on this hand side is the radius always. So here also it is the radius, here also it is the radius. Okay, so this I think it is clear. So now what should we do? So let us see. So yeah, now we can invoke this condition. You see, I proved it for n, I will use it for n minus 2 also. So double integral x1 square x2 square less than equal to 1 dx1 dx2. I've got 1 minus x1 square minus x2 square n minus 2 by 2 v1 n minus 2. So you see what I did here is that I just brought this r power n out and made this v1. So it was using this formula here. Well, okay, now you see we are in a good position to find a recursive relation because you see at this moment this thing is not dependent on x1 x2, it's just a constant. So, and what we can do is, as there are only two variables subjected to this condition, we can make a change of variable as x1 goes to r cos theta, x2 goes to r sin theta. Well, wait a minute. So the square will be 1, so it will so r cos theta or sin theta such that r is less than equal to 1. Okay. This is we make this change of variable. So we may so let's see now. So by using this change of variable, what we can write is this. So let me see. 2 minus r square. Well, I am having problem with space here. Well, okay, I managed. So so you can see that r dr d theta is the this element is the you can transform using even Jacobian. It will produce this, and this one is 1 minus r square because cos square theta plus sin square theta is 1. So that's I think is all right. Now we make one more change of variable. So we say let 1 minus r square be equal to t. So minus 2r dr is dt. So we make one more change of variable. We say 1 minus r square equal to t. So with that change of variable, what we get is that v1 n minus 2 2 pi by 2 integral 0 1 t n by 2 minus 1 dt. Well, now this integral is very easy to perform. Well, did I do any mistake? I think I didn't. Well, okay, so this integral is easy to perform. So what we get is v1 times n minus 2. Performing this integral gives us 2 pi by n. Well, so now you can see already the recursion relation. I'm having a less space here, so the well, let me see. So yeah, okay. So using this thing as v1 here, I can substitute it here to get directly vr recursion relation. So I will just do it here. So the vrn equal to r power n v1 n minus 2 2 pi by n. Well, so you see, we got a beautiful recursion relation between two dimension difference. So this is a recursion relation. Now you can use the formula that I showed. So I just let me just turn it off. So the formula of, you can use this formula and you can plug it in here, and you can find a recursion relation between gamma functions also. Okay, so I think I hope you enjoyed the video. Previous video we covered the volume of hypersphere in terms of gamma function. In this video I showed a recursion relation which can be used to deduce the recursion relation of gamma function. Well, okay, thank you.